Electrochemistry. We talked about electrochemistry last semester a little bit, and we'll see how much you remember because you're going to have to remember some of it. But the point was that you can have some of the most interesting chemistry that's going on inside your body, or if you wanted to solve the world of cancer, develop photosynthesis or synthetic. A lot of this is electrochemistry. And what is that? Well, one compound is providing electrons to the other compound within this chemical reaction. And anytime that happens, it falls into this category of electrochemistry. Not all reactions are like that. Not all reactions are actually transferring electrons from one reactant to the other one. So one producing them, the other one accepting or reacting with the electrons. But the point is if you can identify one of those reactions, like they did inside that Duracell battery, you can use that reaction to produce electricity, right? To run little cell phones or whatever. And so it's useful, but once all the reactants gets used up, the battery's dead. So you either got to throw away the Duracell or get one of those rechargeable ones. Okay. So it takes a lot of juice to get aluminum out of the ground, and that's an electrochemical process. So that's why we recycle aluminum, because it's so expensive. So you save a lot of energy by recycling aluminum. So if you want to be a green dude, that's a good thing to do. Okay. If you don't want your apples to turn brown, put some lemon juice on them. That's an electrochemical reaction. Okay, let's see if we can remember some of this stuff. Let's see. Steph, you see this compound. It's got all this carbon and all this nitrogen and all this stuff. But in that compound is oxygen. And what we did is we assigned oxidation numbers to all these different elements in every compound in the chemical formula. And then we looked to see how those oxidation numbers changed. And that's really how we kept track of these electrons. And they're called oxidation states. And oxygen always had an oxidation state of what number? Close. 2, but it's not positive. It was negative. So these little hints are really important because they're going to help you figure out what the oxidation states of everything else is. Okay. So, and this is pretty much only rules that we really needed to use. And that's why I just wrote these down. It was a big table. The oxidation state of an element in its natural state. Oxygen gas. If I take aluminum, well, aluminum in nature is a solid, liquid, or gas? Solid, so ALS. So anything in its natural state has what? That's an oxidation number. 0. 0, right? When oxidation states of all atoms present in a compound or ion are added, the total is always what? Let's see. If we write a chemical formula, right? A, B, 2, C, whatever it is, yep? If we write any chemical formula, right? What's the number written up here? If it's 0, we don't write anything, right? It's the charge. Right? Isn't that a superscript? If it's an ion, okay, +3 or something. But if you don't write anything, the charge is 0. Remember that? So you add up the oxidation states of everything in this compound or ion, you always get the charge. You always get the charge. So, for example, SO4 -2. You add up the oxidation state for sulfur. 4 oxygens, you better get -2. How about, see if you're following. We have aluminum ion. What's the oxidation state of aluminum? It's 3, right? Well, you say, hey, we said it was 0. No, that's only if it's, right, a solid. Right? And it's a 0. You can kind of also see that, there's only aluminum there. Has to be the charge, 0. Okay. that's the game we're playing. So we'll have plenty of time to practice that some more, especially in the homework. Oxidation and reduction terminology. Again, some review. We use the Thermite reaction, at least they did. I don't know if maybe they still do. It's pretty easy. Join railroad tracks.
Aluminum metal is a very strong reducing agent. The flower pot contains thermite, a mixture of finely ground aluminum metal and iron 3 oxide, plus a starter mixture containing magnesium metal. The reaction is initiated by igniting the magnesium metal ribbon.
Magnesium burns, isn't that crazy?
Some of the molten iron has flowed out through the bottom of the flower pot into the bucket of sand.
But you know, they've never shown that once in a cowboy movie. It'd be so easy to do. But I think people would think, oh, that's impossible. They're welding or something, right? But it'd be cool. That's how they did it. So determine the oxidation state of each element in the below thermite reaction. Okay, Audrey. Pick something here and tell me its oxidation state. There's some easy ones and there's some hard ones. Louder, Steph, louder. Okay, oxygen is always -2. Okay, I'm going to circle my answers because it gets kind of ugly. So oxygen is -2. Do I put -2 over here on the aluminum oxide? Yeah. Yeah. It's always -2. Okay. Keep going, Jose. The oxidation state of something else. Okay, Fe is the reactant or the product one? This one's going to require some math. This one's easy. Product one has to be what? The stoichiometric coefficient, that just means there's 2 irons. Use that to balance it. What's the charge on the iron? What's the number written up there? Nothing's written, so it must be 0. Add up all the oxidation states, you always have to get the charge, right? Well, there's only one thing to add up, iron, so it has to be 0. I'd say there's only one more easy thing left here, Andromeda. Aluminum on the reactant side. It has to be +2. It'd be +2 if I saw that. I don't see that. What charge is written right there? 0. So 0. All right, the rest are going to require some math here, Enrique. See if you remember how to do this. Oh, Enrique, where the heck did you go? Connor, think you can slip out? How are you going to figure out that iron?
3.
Man, he's good. Okay, 3 times, how do you figure it out? 3 times -2 is -6. So whatever you get, that's -6. This is 2 times it, right? Whatever you, could write 2x or whatever, right? Because there's 2 irons. X is going to be, I could write it down here, right? X is going to be the oxidation state of iron, but you have 2 of them. So 2x and a -6, you have to add everything up and get the charge, right? Because 2 irons, 3 oxygens, add it all up, you get the charge, which is 0. So 2 irons, 3 oxygens, add up, you get 0. So 2x and a -6 has to equal 0. He got 3. He's right. X has to be 3. So let's erase that and put a 3. Oh, it's 2x minus 6 has to equal 0. So 2 times All right? It has to be positive 3. Good question. Ask, because otherwise you get lost, you're going to be really lost. See if you can figure out the aluminum. Pretty much the same story, isn't it? All right, because 3 times -2 is -6. So what times 2 is add up to a -6 and you get 0? It has to be 3 again. Okay. When an element gets reduced in a reaction, see if you remember the terminology. Alyssa, when an element gets reduced in a reaction, its oxidation state which one? Oh, this thing got reduced. So its oxidation state got more negative. Reduced gets smaller. It gets more negative. It has to get smaller. That means go more in the negative direction. Element gets oxidized. Kenneth, its oxidation state gets more positive. So oxidize, get more positive. Okay, so that's the first 2 ideas. Reduction and oxidation. Reduction, get more negative. Oxidation, get more positive. Okay, then you have oxidizing agents and reducing agents. They're going to give you reactions. They're going to say, hey, what's the oxidizing agent? What's the reducing agent? Well, if you have no idea, you better guess they're always reactants or products. Which one? They're reactants. Because they're the agents. They're the instituting the change here. They're reactants. Okay, so these reactants. Reducing agents. Now how you figure out which one is which. Reducing agents always get oxidized. That's the trick. Reducing agents always get oxidized. That's how you identify the reducing agent. And again, they're always reactants. Oxidizing agents always get everybody reduced. And they're always what? Reactants. They're always reactants. This stuff is always reactants. So in the above reaction, the reducing agent equals and the oxidizing agent equals. See if you can figure it out. Which one is which? The reducing agent had to get oxidized. The oxidizing agent had to get reduced. I always kind of look for the easiest way out on when I'm doing these. So I'm looking at these oxidation states on the reactant side and seeing how they change. Aluminum is 0. That's kind of an easy number to look at. So aluminum went from 0 to positive 3. So this compound, it went from 0 to positive 3. So aluminum got oxidized. This is the only way I can do this without screwing up. Aluminum went from 0 to positive 3, so it got oxidized. So aluminum is the reducing agent. Okay, and you can do the math and you can figure it out, but you really don't have to. Once you identify one, the other one has to be the other agent. But we can verify it. Iron went from a 3 to 0, so iron got reduced. So it's the oxidizing agent. But you can't write iron. You have to write that whole compound. Fe2, because that's what's containing the iron. And it has to be a reactant. Okay. Now it's kind of nice about this electrochemistry stuff and building these Voltaic cells, and we're going to see what's going on there, but we don't have to worry about balancing this stuff. Before, I don't know if you remember, we had to break things into half reactions, and you had to balance everything but O and H. Remember all this? Yeah. We don't have to. I don't think we need to worry about that. So all we need to do is write the unbalanced half reactions. You don't even have to balance them. What goes to what? You remember how to do this? Half reactions. Megan, what are they talking about?
Aluminum to aluminum.
Yeah, aluminum to aluminum oxide, right? So Al goes to Al2O3. And the other half reaction, Kendall, would be, yeah, the iron 3 oxide goes to, well, just Fe, because we don't need to worry about balancing it. Those are our unbalanced half reactions. Okay, there's two types of electrochemical cells. So there's actually two types of electrochemical reactions, in other words. One is non-galvanic or electrolytic cells. So these types of reactions, again, they involve a transfer of electrons between the reactants. This is called non-galvanic or electrolytic.
A pickle is incorporated into a simple electrical circuit. The forks provide contact between the pickle and the power source. Alternating current will be passed through the circuit.
Essentially just plugged it into the wall. Okay, so they call that an electrolytic cell, plugging in a pickle. So an electrolytic type of reaction is one that happens naturally, or you got to force it. You definitely have to force it. That's the idea of an electrolytic cell. You can get these reactions to go, but you got to force them. Okay? You can't make a battery out of a reaction you got to force. So here's I think the more interesting ones, the ones that are going to happen naturally. Okay, the galvanic cells. You're stuck on a remote island in the middle of nowhere, and you want to get some electricity and charge your cell phone. Well, what do? Build yourself a galvanic, they also call it Voltaic cell. Hopefully they have some lemon trees, and you'd be set. I guess you got to find a galvanic.
This lemon battery is related to the zinc-copper cell. You can build this battery from lemons, galvanized nails, and pennies. How much electrical potential is generated by a 3-lemon battery?
You see what that says? 1.56 or so volts. So that's one AA battery, pretty much. Okay. What are the half reactions in the lemon battery? They said they had zinc and copper. I think it was zinc going to zinc plus 2, if I remember right. Sure. Yeah. So the zinc is coming from, on that island that you get stuck on, you're going to have to find an old fence, and hopefully they use galvanized screws or nails. What all that is they're those silver-looking nails. They're dipped in zinc. They do it because then they won't rust. Okay, and so zinc is going to zinc plus 2, and then the other one. So that's the other half reaction. Is once you stick that penny in the lemon, it's acidic. And it's going to dissolve some of the copper. Not very much, but a little bit. So that copper plus 2 goes to copper solid. And that's a real limitation, because you don't have a whole lot of copper plus 2. So that's kind of what limits your voltage there. But it works. Let's get a bunch of them, though. So there's the two half reactions. What would it look like if you separate the lemon battery half reactions into two different containers? So we're doing something like this.
A galvanic cell consists of two half reactions connected by a salt bridge and an external wire. In this example, a zinc metal electrode is oxidized to zinc ions at the anode, and Cu2 positive is reduced to form copper metal at the cathode. If the two half reactions are connected through a voltmeter, we can measure the electromotive force for the reaction. When connected to a light bulb, the current of electrons flowing through the wire causes the bulb to glow. The anions and cations flow through the salt bridge to compensate for the change in the charge caused by the electron flow.
Okay, what I thought was kind of interesting here is, remember, all they did is they put zinc on the left-hand side and copper on the right-hand side. So this is your zinc solid strip, and you have zinc solution in here that they had to put, right? The other side, here's their copper, and then they have copper ions in here. I don't know if you noticed this. What's this tube, U-tube looking thing? Salt bridge. Now, the only way to understand this, really, is if you, oh, I think they might have, no, they don't. I'm having my guys build little electric circuits over there. Electric circuits always have to be in a complete a circle, right? You can't just snip it, and then the whole thing stops. It has to be a complete circle. So that's, and what's kind of interesting is the electrons, I think, are flowing through that wire, right? But electrons aren't flowing through this tube. Salt is. But it doesn't matter. This is where the physicists, they always say they're the numero uno, and they probably are right, because we follow everything they've kind of figured out. But any moving charge is current. It doesn't have to be electrons. So that's why this has to be a salt bridge. If electrons are going this way, right, electrons are leaving the solution. Well, that means this solution is going to become more positive. Well, then you better have some anion, some negative charge come in here and keep it balanced. That's all that's happening. Right? The electrons are coming over here. Well, this should be getting more negative. Well, no, you get these cations, sodium ions, to come in. So it just keeps everything balanced, a full circuit. Okay. Okay, I changed this a little bit this morning, but it's kind of the same notes you have. Okay. The oxidation half reaction, it's called the anode. It always, Connor, what does it do? The oxidation half reaction always produces or reacts with electrons. You pretty much, I think you got to look back up here to remember this. Which one is the oxidation half reaction? The zinc, because it's getting more positive. Okay. Where are the electrons at to balance this thing out? I don't know if you remember balancing these chemical reactions, but that was the last step. You had to add electrons. Are electrons going to be added to the reactant or the product side? Product. Now, how many of them? 2 of them. And that's just one oxidation reaction. All oxidation reactions, they're called anodes, they all produce electrons. They all produce electrons. So by convention, the anode is always placed on the left. Right? Anode's always over here. It's always the anode. So it's always producing electrons. Right? It's always producing electrons. A lot of them. So then electrons are going to flow from everybody, left to right or right to left? Or are you totally lost? Left to right, yeah, because this guy's producing all the electrons. This one's reacting with them, right? You'd have to have, right, the cathode is where a reduction occurs. It's reacting with the electrons. Anode, okay, that's producing the electrons. So electrons are always going from the left to the right. Okay. And you read your little volts here, right, little voltmeter. So let's draw a conventional Voltaic cell diagram of the lemon battery. Okay, so pretty much you copy this diagram, this little picture, except you need to label which half reaction on the left? The anode. And it's the zinc or the copper? Zinc. So pretty much that's what you do. Oh, I guess it's right here, right? You got the zinc. I guess you have to draw all this stuff. So notice how in the homework, draw a conventional cell diagram. That means do this. We have to draw it all out. It won't look as nice and pretty as this, but that's the idea. Okay? The other option is going to be cell notation, and that's going to be so much easier. But let's do this one first. Okay. So you pretty much need that salt bridge. All right. Need some solution in these guys. We're supposed to have zinc ions over here, right? They're supposed to have copper ions over here. Copper plus or copper plus 2, I'm not sure which one. Remember they had a strip of copper, solid. They had a strip of zinc. Right? I guess we should write it up here, might look better. Right. And then sometimes I write a V with a circle. Stands for voltmeter. So you get the volts. You got to connect it. Okay. And I think in the homework and all of them, they say, hey, indicate the direction of electron flow. So right, electrons are going this way. Okay. What else could they say? They could say label the anode and the cathode. So anode, cathode. Label the salt bridge. Okay, that's about everything, I think, right? No, I guess you could, I don't know if they pick about this or not. They might as well finish it. In the salt bridge, do cations or anions flow out of into the anode? Anions. Think of it this way. You could almost help yourself out by writing this. Zinc solid goes to zinc plus 2. Right? So that means all these cations, zinc plus 2 keeps forming here. Well, that means anions better come out of there. Chloride minus or something. Just write, let's write Cl minus. We call this a sodium chloride salt bridge. And so chloride anions have to be coming out because zinc plus 2 is getting produced to balance it out. Then over here you'd have to have what ions? Cations, right? Okay. Okay, so that's a lot of work. So just hope there aren't too many homework questions that say draw a cell diagram. So much easier to do the cell notation. Okay. So what, does anyone remember this or have you seen it? What do you draw for the salt bridge? They want a double line. And then pretty much all I do is I write, when I do this part, you write the two half reactions, and life is so much easier. Zinc solid goes to zinc plus 2. Copper plus 2 goes to copper solid. And then it's straightforward to write your cell diagram. So pretty much you write the reactants and products for the anode on this side, reactants and products for the cathode on the right-hand side. So you'd have zinc and zinc plus 2. So much easier. The other side was copper plus 2 is the reactant, copper solid is the product. There's only one last thing to remember, and that's how you separate the reactants and the products in the cell notation. Either use commas or use a line, right? So use a line when they're in different phases. Remember, the phases are solid, liquid, gas, right? And liquid would probably be aqueous. So this is a solid, that's an ion, definitely different phases, so use a line and don't use a comma. Same thing over here. A line, because they're in different phases. A lot easier. Okay. Cell notation. And remember, the anode always has to be on the left-hand side, and you'll be set. Okay. Iron reacts spontaneously with copper 2. Obtain the half reactions and describe the Voltaic cell. Well, this is English. Describe the Voltaic cell. So they probably want cell notation, or do they want the nice big fancy diagram? What would you guess? They want the nice big fancy diagram, yeah. So you're lucky, Mia. So draw a nice big cell picture, cell diagram for this. They're going to want to see the direction of electron flows, label the anodes and the cathodes. Don't forget to draw in a salt bridge, all that stuff. Obtain the half reactions. Remember, oxidation goes to anode, and that's always on the left. Right? It's not so bad. You're going to fly in this stuff, right, Connor? It's going to be easy. Easy schmeezy. So have a good day. Don't forget about the symposium tomorrow.